Okay, this is page 75 of the notes on, and this is expected values of discrete distributions. There is a whole lot of scary symbols, etc., but truthfully, this is very easy. We're going to walk through what the calculator does. First, we're going to do it by hand. By hand, this is a bit of a pain, but after we do one by hand, we're going to learn how to do it with the calculator. And this is, I'm going to tell you, this isn't that bad at all, okay? So you're going to have to trust me on this. The first part, when we're looking at formulas and equations, is a little scary, but as soon as we do start getting into the calculator part, you're going to go, that's not bad. That's not bad at all. So expected value. When we talk about the expected value of the mean of a discrete random variable or of a discrete distribution, we're talking about the mean or the average or what we expect to happen. And we use this symbol, the E of X. All right, so E of X is the expected value. Sometimes we will use the formula, the letter M for mu. That's the Greek letter mu. This means summation. This is sigma chi guy, frat boy. So the x's times their probability. Each individual x times its probability. Okay. On the calculator, it's not going to have a mu. The calculator will have an x bar. All right. Standard deviation is really even scarier. And basically, it's the sum of the individual x's minus the average squared, and then we multiply by the probability when we take the square root of that. The calculator won't give you variance, but that's just the standard deviation squared. So it will give you this, and then you'll just square it, and it'll give you that. The larger the standard deviation or the larger the variance, the more spread out the values are, the farther they are on average from the mean. A small standard deviation means, hey, the data is really close to the expected value. The data is really close to the mean. It's not really spread out. A really large standard deviation or variance means it's very spread away from the data. So instead of spending a whole lot of time with the formulas and getting a little nervous about it, let's show you how it works. And we'll do it by hand first, and then we'll use the calculator. So Dell Electronics manufactures computer parts which are shipped to many computer companies. Despite the fact that 2 quality control inspectors at Dell's Electronics check every part for defects before it's shipped to another company, a few defective parts do pass in a shipment of 400. The following table gives the probability of X. Calculate the expected number of defective parts. So the probability we have 0 defective parts is 0.02. The probability of 1 is 20%. Probability of 2 defective parts is 30%. Probability of 3 is 30%. Probability of 4 is 10%. And the probability of 5 is 8%. Please remember, to be a valid probability distribution, every probability must be between 0 and 1. There's no negative, and there's nothing greater than 1. And when we add them all up, so if I added all these up together, they equal 1 whole. And that has to also be true to be a valid probability distribution. Well, here, that's the formula that we had above for the expected value. So let's see if we can do this by hand. Well, 0 times, so I'm basically going to take this column and multiply straight across, and then I'm going to put an equal sign. So 0 times 0.02 is 0. 1 times 0.2 is 0.2. 2 times 0.3 is 0.6. 3 times 0.3 is 0.9. 4 times 0.1 is 0.4. And 5 times 0.08 is also 0.4. If I were to add up all of those values, this plus this plus this plus this plus this plus this, I end up getting 2.5. And that's my answer. That's my expected value. So this scary formula up here just meant do all this work right here, none of which was really hard. Now that was 2.5 defects for every 400. So I'm going to write that down. You had 202.5 defective parts out of every 400. That's what we expect. So in the long run, or on average, that's how many we would expect. So let's go ahead and answer this next question. So how many defective parts would we expect from a shipment of 12,000? Well, in that case, we'd be going, we expect this many, but we're ordering 12,000. So I'm just going to multiply it by the number that we order. All right, and when we do that, I end up finding out that I expect to have 75 defective parts. So that's the answer to that. Okay, so I already told you standard deviation is a bit more challenging. It requires a little bit more work. Again, we're going to do this by hand, and then you're going to see how easy it is to calculate. So first off, x, well, our x was 0. All right. And by the way, we can go 0 minus, 1 minus, 2 minus, 3 minus, 4 minus, and 5 minus, because those are the x's. Well, what did I expect to happen? Well, that's what we calculated here. We calculated 2.5. So I can just put 2.5 all the way down. All right. Need to put parentheses around it. This is going to be very important to put the parentheses because of what we're about to do. All of these need to be squared. All right. So every single one of these differences has to be squared. So when we square that, I end up getting this equals to 6.25. This ends up being 2.25. This becomes 0.25. This becomes 0.25. I need to put an equal sign there. This becomes 2.25. And this becomes 6.25. Now, please note, this ended up being symmetric, but it's not always going to be that way. It's not always going to be that way. Okay, this says we're going to take this difference, because this is the same as this, and multiply it by our original probability. So I'm just going to go 6.25 times 0.02. And when I do that, I end up getting 0.125. I'm going to scoot this over just a little bit so that make sure we can see it. Then we have 2.25 times its probability of 0.2 equals 0.45. And please follow me all the way through this. And I'm going to tell you it's going to be really nice when we get to the calculator, but I do want you to know what the calculator is doing, because I believe it'll help your understanding, and it'll also help you off when you get off to college. All right, and then 0.25, once again, times 0.3, and that also equals 0.075. And then we have 2.25 times 0.1, and that's 0.225. Then we have 6.25, and that equals 0.5. And if I add up all of those values, so if I take all those values right there and add them up, I end up getting 1.45. And that's my variance. All right. If I take the square root of that, I take the square root of 1.45, it's going to be, my standard deviation is approximately 1.204. I don't know about you, but I thought that was a lot of work. Let's see if the calculator can't make this a lot better for us. So here's what I've done. I've kind of worked ahead, so you didn't have to wait on me to input all the data. So I'm going to go to Stat, Edit, and hopefully you can see that I have my data entered, 0, 1, 2, 3, 4, 5, 0.02. Let's see if I can get a little more light on that, see if that helps. Not much. Okay, But anyway, I have all my data entered. So my X is entered here, all the probabilities. All right. Once I do that, I'm going to clear. I'm going to go stat, arrow one space over the word calc, press enter. Now my list needs to be second followed by the number 1. Press enter again. Second followed by the number 2. So it's L1 and L2 because that's where my data is stored. My X's are L1, my probabilities in L2. And look, 2.5 and 2.5, those match. And there's my standard deviation of 1.204. All right, so it did all of that work for me. Now, if I wanted my variance, I'm going to go 1.204. I took the standard deviation, and then I'm just going to square it. Oops. 1.204. I'm going to square it. And there we go. And I know that's not exactly right. It should have been 1.45, but it's within rounding. It's good enough. Okay? So, what is the expected value, variance, and standard deviation when rolling a 6-sided die? Well, first off, I need to talk about the probabilities. First off, I can get a 1, 2, 3, 4, 5, or 6, and each probability is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. So let's go ahead and enter that into the calculator, and I'm going to show you how to do this fairly easily. All right. So, stat, edit. I'm going to press the up arrow, then clear, and then enter. That clears that one out. Up arrow, clear, then enter. That clears that one out. And I'm going to put my X's into L1. 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, 6, enter. And by the way, always put your probabilities or your frequencies in L2. Just make that a habit. Always put the probabilities of frequency in L2. Well, those are fractional, so what do I need to do? I'm going to just put 1 divided by 6, and I'm just going to keep repeating that. 1 divided by 6, 1 divided by 6, 1 divided by 6, enter, and 1 divided by 6, enter. Once I have all those entered, I'm going to go stat, calc, one variable statistics, second 1, second 2, and X, my expected value, or mean, equals 3.5. My standard deviation, please note, this is the standard deviation symbol. My standard deviation is 1.7078. And if you take it out to 4 decimal places, that would be great. So this is my standard deviation. And then we need my variance. .7078. All I did is input it in the calculator, and then I'm going to raise it to the second power. And I get 2.916. All right. I'm just going to round this to 2 places. So my standard deviation, or my variance, is about 2.9166. And that's close enough within rounding. All right, moving on to the next page. So, concessionaires know that attendance at a football game will be 60,000 on a clear day, 45,000 if there's light snow, and 15,000 is there heavy snow. The probability of clear skies is 1/2, 1/3, and heavy snow is 1/6. Do these represent a valid probability distribution? Yes or no? First off, these are all fractional. None of them are negative. So they're between 0 and 1, so that sounds good. So they're between So that's good. So now we need to check to see if they add up to 1. So 1/2 plus 1/3 plus 1/6. When I put those into the calculator, I added them up and they sum to 1. So in this case, the probabilities are between 1 and 0 and sum to 1. This is a valid distribution. What is the expected average daily attendance, variance, and standard deviation for the season? Well, the first time we do a problem like this, it's a little bit scary, but it's really not that bad. First off, we have, I'm going to make my own little table out of this. It's not going to be much of a table. But I have 60,000. I have 45,000. And then I have 15,000. The 60,000 has a probability of 1/2. This has the probability, the light snow has a probability of 1/3, and this has 1/6. Probabilities are always going to L2, so that means the 60, 45, and 15 going to L1. So stat edit, press clear, then enter. Oops, arrow up, clear, enter, arrow up, clear, enter. And we're going to go 60, 1, 2, 3, 45, 1, 2, 3, 15, 1, 2, 3. 1 divided by 2 or 1/2, 1 divided by 3 or 1/3, 1 divided by 6 or 1/6. And once again, average daily attendance, so average, variance, and standard deviation. So here we go. Stat, arrow over to the word calc, enter, make sure it's second 1, second 2. And our average equals 47,500. I'm going to STD, standard deviation, is 16,007.81. And then our variance is our standard deviation squared. So 16,007.81, and I'm just going to square it, is 2.56. Wow. Actually, that's going to be a lot bigger number than that. Got to put some zeros in there. That's in scientific notation. So this is 256,200. You know what? I'm just going to leave it in scientific notation. That's good enough. 2.56 times 10 to the 10th. That'll work. All right. And if y'all want to leave it like that, because generally speaking, I'm not going to ask for something like that. Okay. All right. So a manager must choose between 3 options and wants to choose the one with the highest return. Which option should they choose? This is a confusing problem because people want to combine things, and we can't do that. We got to look at them separately. So we can get 250,000, or we can lose 10,000. This is 0.9. This is negative. This is 0.10. I swapped those. Be careful. Don't do what I just did. Probability of that is 0.1. The probability of losing 10 is 90%. 10% chance of getting 250, 90% chance of losing 10,000. For B, we can get 40,000. The chance of that happening is 50%. And we have a 50% chance of losing. And then for option C, we have a 5% chance of getting 800,000 and a 95% chance of losing. So let's do the expected values because they want to know which one should they choose. And they said, what's the highest expected return? So we're going to have to do this 3 times. So 2, 5, 0, 1, 2, 3, and oops, stat edit, 250. And make sure you use the negative sign, not the minus, use the negative sign. Negative 1, 0, 1, 2, 3. Enter. And then we have 0.1 and 0.9. Stat, calc, one variable statistics. Already have the L1 and L2. So in this case, we expect to get $16,000. So if we did this over and over and over again, sometimes we're going to win 250, sometimes we're going to lose 10,000, but on average, it's 16,000. Over here, stat edit, and I'm going to go ahead and clear everything out. 40, 1, 2, 3 for 40,000, and then negative 2,000. Being careful to use the negative sign, 0.5 and 0.5. Oops. Better clear all that out. Okay, 40, 1, 2, 3, negative 2, 1, 2, 3. So 0.5 and 0.5. So 50% of the time we win 40,000, 50% of the time we lose 2,000. Stat, calc, one variable statistics. Once again, making sure we have L1 and L2. In this case, we have an expected, we expect to get 19,000. So we know B is better than A. And then we go to C. And boy, you can win big here, or you can lose. You can win big or you can lose. So here's what happened. And we find out that we end up with an X bar of 21,000. So the average, so if we did this over and over again, we would expect a return of 21,000, which is greater than this. So we would choose option C. Option C would maximize our return. That said, 95% of the time we're going to lose 20,000, but because we win so much 5% of the time, it's worth it if we can stay in business long enough to do that. All right. A highway engineer knows that his crew can lay 5 miles of highway on a clear day, 2 miles on a rainy day, and 1 mile. Suppose the probabilities are as follows. Okay, remember, frequencies always go into L2. So this will be L1. Probabilities of frequencies always go into L2. So let's go ahead and do this problem. Stat edit. And we end up with 5 enter, 2 enter, 1 enter. 0.6 enter, 0.3 enter, 0.1 enter. Stat, calc, one variable statistics. We already have L1, L2. And so we expect, on average, in the long run, our expected is 3.7 miles. This is the mean. Our standard deviation, and that symbol is this, ends up being 1.6155. And our variance is just this squared. So the 1.6155 squared. And we get 2.609. All right. And that will take care of expected values.